So in the previous lecture, we have studied about the quantization and the process of quantization with the help of example. So again, to summarize, the quantization is the process of assigning a nearby voltage levels to the flat top samples or any type of sampling which it is done. And we have discussed that when you are assigning a quantization levels, that time there is a difference between the quantization levels and the assigned quantization levels and the original magnitude of the signal. And that particular we have highlighted as a quantization error in the previous lecture. So the difference between the rounded values and the original value is called as quantization level. And we said that when you are assigning a PCM code with more number of bits, then quantization error can be reduced. So here is the example of the quantized signal with different number of bit depth. If bit depth means the number of bits which it is assigned to each and every quantized level. So in the figure A, you are saying that bit depth is of 2, means 2 bits. The PCM code will be of 2 bits and that will be assigned to a level. So red line indicates that it is a sample value, that is your original signal. Black line indicates that it is the quantization value and the green line indicates that it is a quantization error. So you can see when you are assigning a 2-bit PCM code, that time you can see there is a difference between the quantized signal as well as quantized signal and your original signal, and therefore quantization error is more. In the figure B, you are able to see that bit depth is of 3 bits, means the PCM code will be of 3 bit. So you can see there are more number of quantization level and therefore the quantization error is less as compared to figure A. In the figure C, you are able to see that you are assigning 5-bit code and therefore the quantization error is still reducing, and in the figure D, you are able to see that quantization code, that is PCM code, is of 16-bit and therefore you can see there is very less error, you can see negligible error, and your original signal and quantized signal looks similar. So there is a relationship between the PCM code and the quantization level. So if you have more number of quantization level, you will be able to represent that with more number of bits, and therefore you will have improved resolution, and therefore quantization error will reduce and there will be no difference between the original signal and the quantized signal. So always it is advisable to use more number of bits for assigning, more number of bit PCM code for assigning to a quantized level, and that is explained with the 4 different figures in this slide. Now we are concentrating on the types of quantization. So we are going to explain 2 types of quantization. One is called as uniform or the linear quantization, wherein the quantization levels are uniformly spaced, and the quantization intervals are coded in the binary form. So each quantization level will be in the power of 2. For example, in pulse code modulation, we are using 8-bit code and therefore 2 raised to 8, powers of 2 I said. So in PCM, we are using 8-bit code. So 2 raised to 8 will be 256 interval for quantizing. So there will be total 256 quantizing interval, 128 in positive direction and 128 in negative direction. So in the linear quantization, you will have equally spaced, or you can say uniformly spaced quantization level. It does not depend on what is your analog signal, what is your input signal. Irrespective of that, you will have uniform quantization, and the diagram for uniform quantization will be this. You can see each and every step size. Why I am talking about step size? Step size is nothing but our quantization level. So each and every quantization level is uniform in the positive direction and negative direction. X of t is the input, y of t is the output. So this is a kind of transfer curve, transfer characteristics for uniform quantization, and the levels are always in the power of 2. If it is 2-bit code, then it will be 2 raised to 2, 4 levels will be there. If it is 8-bit code, 2 raised to 8, 256 intervals will be there. But what is the disadvantage of the uniform quantization? That it does not see what is the input signal, and therefore there will be huge quantization error when we go for uniform quantization, because our input signal will never be uniform. For example, if we consider speech signal is continuously varying signal. So if we go for uniform quantization, then it will have large quantization error, and therefore we are going for second type, which is called as non-uniform quantization, also called as non-linear or logarithmic quantization, wherein the quantization levels are unequal, and mostly the relationship between the quantization level is logarithmic. And this particular quantization is applicable to a speech waveform or the sampling of speech waveform, because many of the speech signal will have non-uniform distribution, and therefore the amplitude is more likely to be close to 0 than the higher level. So the speech signal will be having any nature. So you can see this is the graph for non-uniform quantization. The step size is very small when you are close to 0, and it is increasing logarithmically or non-linearly when you are going towards higher side. So this is the input sample, this is output sample, and non-uniform quantization will be looking to an input signal, and according to that it will be adjusting its step size, and because of that non-uniform quantization is preferred for all the types of speech signal, and it does not have quantization error will be very less in case of non-uniform quantization as compared to a uniform quantization. Now, in this slide, we are explaining the relationship between step size and the quantization error. So, for example, if the range of the input signal is from minus x max to plus x max, then the step size can be calculated as positive value minus the negative value. So x max minus of minus x max, which is equal, divided by q. Q is the number of quantization level, which is equal to 2x max divided by q. If our x max is equal to plus or minus 1, then our delta, which is nothing but our step size, which will be equal to 2 by q. The maximum quantization error, which can be epsilon max, which can be allowed, is plus or minus step size by 2. This is the maximum quantization error. So the step size can be calculated by the range. Range means positive maximum value minus negative maximum value divided by number of quantization level. In some books, it is also written as divided by 2 raised to n minus 1. So if we have 256 quantization level, then it will start, then here denominator it will be 255, because we are starting from 0 to 250. So that is what is the number of quantization level. Now again, in this particular slide, it is explained with the help of example. Suppose our maximum input voltage is from 0 to 5 volt, or it will be minus 2.5 to plus 2.5. We are having a peak to peak value of 5 volt. So positive may plus 2.5, negative minus 2.5. Number of bits which are assigned per sample is equal to 8 bits. Therefore, the quantization level will be equal to 2 raised to n, that is 2 raised to 8, which will be equal to 256. So our delta will be VH minus VL. VH is positive maximum, VL is negative maximum. So for our case, it is 2.5 minus of minus 2.5 divided by Q. Q is nothing but 2 raised to n minus 1, which is equal to 5 divided by 255. 256 minus 1 will be 255. If we calculate that, it will come as 19.53 millivolt, approximated to 20 millivolt. And if our sampling frequency is 8 kilohertz, then the bandwidth to transmit this particular signal will be equal to n into fs, where n is nothing but our samples. Okay, that is a quantization level. That is number of bits which you are assigning per sample, that is equal to 8 multiplied by 8 kilohertz is the sampling frequency. So 64 divided by 2, which will be equal to 32 kilohertz. So this particular signal can be transmitted with the help of 32 kilohertz, and that will be the bandwidth to transmit this particular signal. So there is a relationship between the step size and the quantization error. So if you see this particular formula, if your quantization levels are less, then you will be having a step size higher, and therefore you have more quantization error. And if your quantization levels are more, the step size will be lesser, resolution will be better, and therefore quantization error will be less. So always it is desirable to have more number of PCM bits, more number of quantization level, more resolution, so that our reproduction of the original analog information signal can be done easily. In the next lecture, we will be able to see the block diagram of pulse code modulation.